Okay, and you can see tonight there's like a skateboard and a scale sitting on the prototype 2, like taken apart. So what I did is I took the middle section out that had the blade and the track and all that, and the track on there is like some thin sheet metal. And anyway, I weighed it, and since it was hooked with a wire, I had to lay my first skateboard across the thing, and then use the scale, and I came up with 22 pounds of weight. So what I want to know is, like, how small of a rod can I get away with for the actual track that the blade carriage rides on. And the issue is this: if the blade carriage, well, the blade has the motor has like an aluminum block that you bolt to. Let's try to draw it here. And if that's running off a rod, and then there's the thickness of the table, which, for prototype 3 I'm thinking about using some melamine laminate. Okay, well, this, whatever this is losing actual amount that this guy sticks up, the actual blade sticks up. So I'm losing capacity that way. So I want to minimize this rod. I'm not sure if I can minimize the other very much, but I can minimize the rod. So how do I do that? Well, what I need to do is think about what we used to do: a free body diagram of a beam under a load. We'll just call it W, even though we know it's 22 pounds. And then we've got, the actual supported weight on the ends, which would be, of course, W over 2 and W over 2. Alright, and this is going to try to bend the beam, but we want it to, not. So, what diameter beam will not bend and not exceed max stresses in steel? So, for our purposes, it's easier to use a solid rod. Not so much for the calculation as much as a solid rod is going to be the smallest thing that's the strongest thing. If you use a hollow tube, you would actually get more strength for the weight, but we're more concerned on this particular member with the diameter, making the diameter small. So we'll just call it diameter D, because D is what we want to find. Alright, and so the equation for max compressive stress, you see, when this bends, you can imagine it like, let's try to draw it. Let's say it was like this. This is the neutral axis, and even when it bends, the neutral axis doesn't distort at all, but up here it gets compressed and down here it gets stretched out. This is in tension, this is in compression. So what we want to know is the maximum stress in the beam, and the equation is pretty simple. It's the bending moment, and we'll talk about that in a minute, times y, we'll talk about that in a minute, over the moment of inertia. And moment of inertia is just a representation of how the cross-sectional shape of the beam affects the the bending strength. So for a solid tube, it's pi over 4 times r to the 4th, and which in our case is d over 2 to the 4th. Alright, simple enough. Y is just the distance from the neutral axis to the point of maximum stress, which would be the edge along the bend, or you can think of it from here to here. In that case, it's y is just d over 2 as well. Alright, and to find our bending stress, we can, since we want the beam to be 24 inches, then we can think of it this way. Here's the weight here, and this would be 12 inches, you know, half of it, and here's our W over 2 here. Okay, so this is obviously going to try to spin it like this, and so that means that the actual internal stresses in the beam right here spin it the other way, like that. Okay, so that gives us a moment. And remembering our equation for moments, leverage is just the distance times the force. And since this weight here is irrelevant to this moment, it's not creating a torque. This one is. It's actually W over 2 times 12. Or in our case, 12 inches. Alright, so we just plug that in. W over 2, 12 inches. Okay, so now we want to take this guy and simplify him and sort of get D all by himself, where we can figure out, you know, ultimately what we want to know is, what do I need to buy? What diameter tube do I need to buy? So we leave this, and let's do some, you know, some old school algebra, right? 8th grade, right? Alright, first thing we can do, turn that into 6, and then that's gone, that's 3. Alright, so let's rewrite it, and we're going to separate the variables from a constant. It just makes calculations easier. So the constant values are W and 6 inches, and then pi over 4, and then times 1 over D cubed, and then we'll go ahead and cube the 2 to make him 8. Alright, let's just simplify a little more. The 4 here, you know, goes to the top, so you get 4 times 6 is 24 inches, W over pi. And the reason we're carrying the units around in these constants, in this constant term, this constant there's no variables, so we know what W is. These are all just numbers. The reason we're doing that is because we want to make sure we don't mess up, and it's a kind of a tool. You should get inches. We should get D, just in plain old inches, not inches cubed, not inches to the thousand. You know, inches. So anyway, this guy right here gets inverted, and it becomes 8 over D cubed. Alright. So let's go back up. We'll keep that one on there so we don't forget it. Alright. And so you're going to get 8 times 24 inches times W all over pi. And that's going to be our constant. Times 1 over D cubed. Or we could do it like this. We could just say the constant divided by D cubed equals sigma. That's the real equation. Alright. So let's find out what that constant is. And so what we do, 8 times 24 times 22 divided by 3.14, and we get C equal to 1345 basically, and that would be 1345 inches times pounds. Alright, divided by D cubed equals our stress. Now for us, we're just going to give the steel a stress value of 60,000 kilo PSI. not 60,000 kilo, 60,000 pounds per square inch, 60,000, 60 kpsi. Now, for the unit stuff, let's just go ahead and put it the way it really is. What psi really is pounds over square. Alright, so now what we need to do is we solve for d cubed, and we get d cubed, and you multiply this side, then you divide back by that, and you get, well, you divide back by this. Ooh, that would have been bad. So anyway, you get 1345 inches times pounds over 60 k pounds over inches squared. Whoop, squared. So what that means is this goes up here, and that it goes away, and we just get inch cubed up here, and then these cancel out, and we're left with that. And so once you take that to the 1/3 power, or cube root, however you want to say it, this becomes inches. So that's a little bit of a check. You can still make mistakes. I think I made a mistake last time. Forgot something in the constant. But anyway, what we get is our diameter equal to whatever that is. So I'm going to plug it in, 1345 divided by 6,000. Alright, and then we're going to raise that to the 0.33333333 power of the 3rd power. And we get 0.282 inches. And the reason I took it out to the 3rd decimal is because most of these, inch, you'll see, like when you divide them, they usually come out to something like that. So let's see what 5/16 rod, I think, okay, that's 0.31, 5/16. Alright, and that's 5/16 is 1/8 more than 1/16 more than 4/16, which is 1/8. So 1/8 is 0.125. So again, 5 divided by 16 is bigger than we need, and 1/8 is smaller than we need. So what that tells us is that we should be fine with 5/16 diameter solid rod.